Let's talk about op amps. Let's talk a quick review. We've got this op amp, and we know that all op amps should have some sort of negative feedback. I'm going to draw it as a question mark, just something connecting the output to the inverting input. What are the two rules associated with op amps, with op amp analysis? There's two of them.
Nodes, their voltages are equal.
V plus equals V minus if there's negative feedback. Yeah. And if those V plus wasn't equal to V minus, the output would swing wildly to enforce it to be V plus equals to V minus. And that feedback can be anything. It can be a voltage source or a current source or a resistor or a capacitor or a cow. Whatever it is will ensure that the output, what the output does, will feed back somehow through this to the input. What's the other rule? One rule is that
going into the output.
I'm sorry?
Be going into the inputs.
Ah, okay. So let's talk about that analysis method. So the smart analysis method is to do KCL at the inputs and never KCL at the output. And that's because what's not shown in this diagram is that in fact there's power connections here, and those power connections can push current in regardless of the can push current out regardless of the current in, which is the hint for the second rule, which is
that the current goes in equals the current goes out.
No. So what Connor said is that it's got to obey KCL because the current that goes into it has to be the same as the current that goes out to it. So if you sum the two inputs, it has to be equal to the output. And that is not true. But the reason why that's not true for an op amp is that there's these hidden power sources that power this op amp. So you can have, so it does not, so if you to draw a super node around your op amp, around here, that does not have to obey KCL because it does not, the entire true op amp that shows your power sources here and shows your power sources here, yes, that has to obey KCL. But because those power sources are not drawn, KCL is not true for just these three leads. Was that what you said, Connor, or did I misinterpret it?
Yeah, that makes sense.
But there is a second rule, and it has to do with current coming in. It has to do with currents. What's that second rule?
Doesn't go into the inputs.
That's it. The current that goes into the positive input is 0, and the current that goes into the negative input is 0. The current that goes into the op amp is always 0. There can be current that comes out of it. And that's why you always do KCL at the inputs, because it's really easy. There's no current that goes in, and you never do KCL at the output because you can't tell what the current is coming out of there. Given that, let's do our first op amp example, and I'm going to give this example with an RA. I'm going to make it a very general circuit. We've got a feedback resistor, and to make it a little bit tricky, I'll have it attached to an odd type of VS. Here's our output. And now let's talk about what the different parts are. For this particular example, I'll make RA 20K, RF 80K, make our capacitance equal to 5 microfarads, and our source voltage equal to something involving U of T's. And I need to tell you what you need to find, which is V naught. You guys remember the steps for solving any first order circuit? Let's hear it. Who hasn't said anything? Philip.
So the first step is to find V out when the time is less than 0.
Right. To find VC naught, or equivalently I L naught. And you'll do that, like you said, for time less than 0. And Philip, I should know, I've known you now for over a year. Do you prefer Philip or Phil?
Either way, Phil is my basketball coaches call me, but everyone else calls me Philip. I don't really care.
Okay, we can go with Philip. Ben, what's the second step?
Like the voltage when t equal infinity.
Yeah, you can do that. You could do that as your second step, but I usually call that my third step. That's VC of infinity, or equivalently I sub L of infinity, and that's for time equals infinity. You want to draw it. How about what I usually call my second step, John?
Which one?
So when you're solving first order, which one do you mean, for a capacitor?
Which
or for
John?
No, which John?
Oh, John. Yeah, that's right. We've got a couple of them. So I thought that the other John was Jonathan. Do you go by?
That's true.
Okay, so I'm gonna call you John.
Most
Mr.
people
Barker.
shorten it to John, but you can call me Jonathan or John. Either one works.
Okay. Oh wait, most people call you John.
Yeah.
You're going to be Jonathan for me, just to differentiate.
Okay. Sounds good.
I've got lab partners, which are my two Charleses, and I've got lab partners, which are my two Johns. But I'm going to call Jonathan and John. Okay, so John Barker. What's that second step?
Isn't it when you finding when t is greater than 0?
That's right. And what are you trying to find when t is greater than 0?
When I is 0?
No. That's your very first step, is to find I sub L or V sub C, depending upon if you've got a current, depending upon if you've got a capacitor or an inductor.
Mm-hmm.
And that's for time less than 0. So that's that DC steady state. And then it's also DC steady state. Did I write it at 0? Holy cow. I need more sleep. This should be at time equals infinity. You're at DC steady state. To find VC of infinity, or I sub L of infinity. But when you're drawing it for time greater than 0, you're trying to find something specific. What is it? It's not a current. It's not a voltage. It's...
I don't know what it's called. But looks like a T, but there's no top to it.
That's it. That's
Tau.
the tau, the time constant. That's it. Okay, and then your fourth step is to find is to plug it in your standard formula. So for VC, it's V of infinity. I'm just drawing the lines at top and bottom to show that these are DC values, plus V naught minus V of infinity, e to the minus t over tau. And there's a version for inductors too that's the same thing. It's just using I's instead. And then our fifth step is to find what you're asked to find. So what I didn't mention is that no matter what you're asked to find, you're going to find V sub C or I sub L first. And only at last is if you're asked to find something else, will you find it. So armed with those steps, let's start off analyzing this circuit. So our first step is to find VC naught. So we're going to have to draw it for time less than 0. When you're drawing a circuit at time less than 0, no capacitors, no inductors, their opens or shorts, no switches, their opens or shorts, no U of T's, they're zeros or ones. So let's draw it quickly. We've got our R sub A. What does the capacitor become?
An open.
An open. Uh-oh, you've got a problem. I said to find VC, but there's no VC anywhere. You've got to notate it. Because if you notate it in this way for problem 1, and then in problem 3, part 3, say, you flip the signs to this, you're going to get wrong answers. And it's really easy to flip signs. So write them in every step of the way. So this is going to be VC. And I just chose the sign convention arbitrarily. You'd be perfectly fine if you chose it the opposite way. So this is minus plus. What's the voltage source?
Would it just be 3 volts?
Just 3 volts because that U of t is 0. And I'm drawing V out, but I really don't care what V out is. Remember, our goal is just to find our VC naught. So VC in this time region is VC naught. Let's analyze it. This looks a little complicated. My first step when analyzing any circuit is to look for current flows. And I want some current flow that involves VC naught. And this would involve VC naught. I know it's 0, right? It can't go over an open, but I still want to draw it in a loop anyway. And I could draw it through my op amp. That seems more complicated. A faster way is to just draw it in that circle. So if I draw it in that circle, I want to find VC. What are my rules to find VC? I can do nodal, mesh. These all seem complicated. How about just...
Well, can't you just say that VC
Yeah.
be -3?
Yes.
Those
Why?
two nodes have to,
What rule?
I think it's the first op amp rule that V plus has to equal V minus.
No. Right answer, but wrong reasoning.
Wait,
So
sir.
just because you know that this node here, and you do know that, is 3 volts relative to ground, that doesn't mean this node is 3 volts relative, is 0 volts relative to ground.
Wait, sir. So if that's 0 volts right after RA, and it's the node.
Why is it 0 volts after RA? You're right, but why? Why isn't RA? Why doesn't it drop some voltage? Why isn't it 2 volts across RA?
It's connected to an open.
Right, because of Ohm's law. Ohm's law says no current, so therefore no voltage. So now we can use what you just said about, so it's a bunch of things where we know what this voltage is, we don't know what this voltage is, we know that this voltage is 0.
Colonel Squire,
Yeah,
just wanted to let you know that John Barker's computer crashed, so he's joining me on my screen.
okay, fair enough. Sorry, John, it's always like that. There's always problems with the internet. So let's do what I hear everybody doing, but they're just not saying the words, is KVL. They're doing a KVL around this loop. And so starting it right here at the bottom of RA, they're saying this is -0 plus VC plus 0 plus 3 equals 0. So therefore VC is equal to -3 volts. And maybe what some of you were saying, and I just misinterpreted what you were saying, was that because this is 0 volts, this is like a short. And so you could put your fingers on the +3, carried up to the minus, put your fingers on the minus, go right through the RA since it's 0 volts, connected to the plus VC. And since 3 is now connected directly across VC, just in the opposite polarity sense, intuition says it's equal to -3 volts. So you can do it either using intuition. It requires a pretty advanced sense of intuition, though, not to get messed up, or doing KVL. But either way, that works. Questions about that first step?